So if you're wondering like why I'm still speaking and you're still seeing this on screen, it's because I wanted to just continue and finish off the spring damper, the suspension system. Right, so this, by the way, anyone, I will be uploading it. You can take a look at it and see what you think. This has just been a typical example of how you set these ones up and how these ones work. I'm just going to close some of this crap that I've got going on in my background. So let me just close that. I'll save that because it was painful enough to get the damn thing working. On Teams, so let me just open up Teams. On Teams, I know, Damien. Yeah, I know. It's once I came off yesterday, I looked and I thought, oh god, that's such the best way of solving it. And once I sat back and thought just about misalignments, because it was obvious between you and Theodore Logan yesterday, you were able to really iron out the fact of that it was such a crap model. Right, so 2 seconds. Let me just show you this. So on here, on Teams, on Files, on Class Materials, I've actually uploaded Gearbox. It's just so you know that the model's there. And what I'm going to do is, I just want to open this model. I'm going to show you this gearbox cost. It looks worse than what it is. So let's just take a look at it. It's one that I saw this morning, and I thought, yeah, it's not bad. It's actually not a bad example. There's a few bits that I kind of thought, oh no. So first things first. What I personally do with these, and what I did this morning, was get annoyed. No, what I did this morning was I looked at it and we have the bearings. Now obviously with bearings I'm going to drop all my bearings off because I don't really need them. So I'm going to hide that. Then we've got the housing. We can stick the housing in afterwards if you want, but it would only ever be aesthetics. So what we've got now is the basics of this system. We've got just the gears, we've got the keyways, but you'll notice the shafts have a way of interfacing with it. What I'm going to do is build each one up, and we're going to have to essentially tell the system that these two parts are not one part, they're actually two parts working together in a single assembly. So first things first, I'm just going to come out here and just pop that there for a second. Right, so I'm not going to give you that one just yet. Like I said, I was working through this morning, and I think I've come up with a nice little way of delivering this to actually make everyone's lives so much easier. I hope so anyway. So you will become an ultimate expert at rigid transforms by the end of this. Promise you that one. Right, so I've got the gears, everything's all in here. All these lower steps here we've actually got already. I'll explain to you where the PCDs have come from, and by the end of this I'll upload everything that's here, and you can have a play around, see what you think. But these gears are really useful. Found some really fascinating things this morning actually. What we'll do is, let's start a new one. So we're into a new part. And again, if you're after these models and you do want to follow me, you are more than welcome to download the parts. So I'm going to go as normal, library browser. Scroll down, and all I'm going to do at the minute is start my world. Let's go on to there. Start my world. So I'm going to go utilities. As ever, we need a solver. I'm going to go frames and transforms. I'm going to bring in a world. And as ever, this becomes our base construction area. So, coming back up, on the SolidWorks model, I am just using this as a map really, just for me to see what's going on. I'm going to start, if I click on here, this is my output shaft. I'm probably going to start on the output shaft, because in my example, what I thought I'd do is I'd spin up the output shaft to see what input will be needed to get a value I'm actually creating here. Thought it was just something different. We can do it the other way around if you wish, but that allows me to do that. And then what I can do is I can look at what happens if these gears become jammed, if they've got mass levels of drag on them, if there is major issues coming out of these. We can do all sorts. So that's what we'll do. And let's pretend for this example that we're looking to try and find any abnormalities that occur. And we'll make it similar to the actual assignment. So in this case, we'll try and chase the idea of if there is some type of noise that's coming from it. So what I'll do is start on my output shaft. I'm going to on my output shaft. So what I prefer is, now a lot have done this on the gearbox themselves. A lot are actually trying to construct this as one big massive hit. Wherever there's a gear, there must be a gear touching. Even if the gears aren't touching, they are touching. There's gears everywhere. It's like rein it in a bit. Deep breath. You don't need all that to do that. The truth of it is the construction behind this. I'm after first gear. Perhaps go for second gear as well. I'm third gear. But actually, at one point in time, there is only one gear touching. There is only one gear interfacing. It's a configuration. So if that configuration changes, I don't need it live changing. It would be ideal to look at different ones, but you can do live changing. But I'm not going to do that because that will make your assignment really, really difficult. And I'm starting to think that'd be a great project, actually. Right, into the world. I'm getting on a tangent, as ever. It's me. If I'm your project tutor, you will know that. I'm going to drag and drop a Revolute joint. And we're going to start with our output shaft. Snap that in. And what I'm going to do is build to there. So, I'm going to go to... Where are we? Bodies, and I'm going to bring in a solid. Then what I'm going to do is I just want to bring in that output. I want to bring in that output shaft. Double click into the output shaft. And what we're looking for is the slot and the keyway. There we go. That's our output shaft. To see that there is differences, because don't forget we're going to bring these parts in first time, all the same colour, and they're going to be swallowed up. We need to be sure that we're looking at the right stuff. So I'm going to decide all my shafts will be blue. My inertia, sorry, I'll go custom density, and I'm going to go 85,000. 8,500, not 85,000. And then go graphics, and I'm going to change that to blue. Any blue will do. It's just to have that difference. And I want to look at my reference points, look at my frames. And you'll notice that on the keyway it actually does have a point already. What I'm going to do is I'm going to select the end face and create myself a point there as well. Because what it'll allow me to do is give a point, if you will, an origin, a reference to start building from. So I'm going to go frames, add in the frame, and I'm going to go, we'll go main or something like that. It just gives me a point to begin my referencing. So I go select. Because the way that the guy has drawn this, he's actually done it. To be fair on this guy, he's actually done a pretty good job. He would pass in his assignment. If I click save, and then apply, and then OK. So what we'll do first is we'll flip it round, get this connected. As ever, I just want to make sure that there's nothing that I've missed there. Just going to run it in. As you'd imagine, there's nothing going to happen. There's no activation. Activation. There's no there's no real rotations or anything there. I'm going to move my my gravity into Y and shift that there like so. And bring that down. Then, now, what I'll do is I'm going to bring in the gear, and then we're going to look at why it's wrong. It sounds really bad, that, and I don't mean to make it sound like that, but we're going to bring in the gear and just make and like I said, make a look, have a look at why it's actually going to be wrong. So I'm going to right click, and sorry, I'm going to double click, and I'm going to go to what is actually gear 1. So let me just let me go turn details. Just want to sort this by type. It's irritating me. Sort by type. So I'm actually going to go output gear 1, F5, and bring it in. It's our gear. Then I'm going to go. I'm not actually going to change the colour. Big gears I'll leave. Small gears I'm going to have them as red. So I've got a nice overview of what's happening. And I'm going to come into my gear, my ratio here. That's actually fine. And then all I need to do now is just update my densities. Everything's set to that with mine. I've automatically set it like that. You don't have to, but I mean I've done it like that just because I got sick of it being set to water or air. So I'm going to set that like that, and then I'll just call it big gear. What we're after doing, setting up the first relationship between it. Setting that relationship will make life so much easier for us. But first things first, let's connect that up. And I'm just going to hit run. Now, let me have a go. This tool is, I can toggle center of gravity. Center of gravity on this is referring to this being a central part, as one piece. Really, each component has its own center of gravity, but these two work together. So what I actually want, for a bit more accuracy with this, I want these two to be separated, but not lose that relation, if you will. So I'm going to close that, and in here, I've alluded to this a few times, I don't know who's used it yet. I'm going to use a weldment, a weld joint. This literally just allows that centre of gravity to still be representative within each component. So if I run it again, God damn it, there we go. Wow, that's actually not showing me anything now. Brilliant. Brilliant, that's actually not showing me anything. In essence, It should allow me to at least see the difference that they're sitting there, but it didn't actually show me that, which is a pain in the arse. Anyway, doesn't stop us from moving forwards. Bring this back a little bit more. Right, so we've got the big gear in position. Now, I'm going to bring in the gear tool. So let me just find it. Where is it? Gears. Yeah, sorry, yeah, gears and coupling. Now what I'm going to do is I'm going to use a common gear constraint. This refers to just a gear and it's the relation between it. So there's a few ways of doing it. I'll show you how I've done it. It doesn't mean it's the only way you can do it, but I'll show you how I've done it. So first things first, you got to go into what you're looking for. So I measured both of these. I measured the big gear and I measured the little gear, both big and, well, mid and to large gear. Both of them. This one, PCD, actually measured at 58.5, and this one measured at 18.5. I think I did a slight mix up on there, but it's nothing that can't be modified. So what I mean is, if I come in and then type, we have two multiple choices in here. We can either go external or internal gears for planetary gearboxes. We can go center of distance to the ratio, so center of distance between the two, and then the ratio of the gears. Or we can go pitch circular radii. So we go the base gear. In this case, it's the big gear that's following. So all I say is 58.5. And because it's after the radii, not the diameter, I go over 2 in millimeters. Repeat that process again. We're going to go 18.5 over 2 in millimeters. Now I get dead excited with all this, I really do. Is there any questions on this so far? Anything that you're unsure about? Anything you want me to do again? Good, right, okay, so let's move on. As ever, if there's anything else we're going through, stop me, make a comment. Honestly, I don't mind. I prefer it. It promotes just discussion. And that's what this should be really about, just the discussion. Now the configuration I've got here, I've got the same. So I'm going to right click and just drag across. Might as well. It's going to work to my advantage. And I'm going to rename that small gear. Double click in. And within the small gear, let's have a look. What was it called? It's called middle gear speed shaft 2. Apply. Let's have a look. F5. There we go. Right. Now again, there's relationships going on between the gears, between the shafts. What I want to do is change this colour, or else I'm going to lose a lot of what's going on. So I'm going to drop that, drop to here. And for me, as I said before, I'm going to change that to a red. Click apply, F5 that, and set and apply. So we've now got that. We're operating with some level of decency with it, which is happy days. If we just look at the R gives us that origin. So this is quite nice. We've got a measurement between it. What we are going to have to do is translate this back, if you will. So I'm going to just bring this in. Don't run it yet because it's still going to crash. There's no real definition of where this gear sits in space. So it's going to have a bit of a meltdown. So I'm going to go joints. And I need to close this joint. So I'm going to go to Revolute joint, bring that in, and zoom it and revolve. Bring that round, pop it in in relation to here, and finally, like the piston, like the suspension, it needs to be able to find its home. If it can't find its home, it will have a model violation. So what we actually do is we need to translate these offsets back along here. However, the other one is on the gear itself, we need to translate this shaft, because if you remember, we were using the end of this as a measurement. So I'm going to measure between here and here. Then if I bring in the normal distance of that is 40 millimeters. So then it tells me that I can translate that 40 millimeters back. So let's bring that translation back, and then what we'll do is we'll move on to the next layer of gears. Now, one thing you should be really starting to notice is these gear constraints are only used if there is direct connection between it. If you're in first gear, it's not going to be working, so it's not got a relation. So then the drive behind this becomes the main shaft, not the gears. So this becomes a configuration. Like I said, to run it in first, second or third, it's a configuration of them gears, and that's why this assignment in particular is quite tricky, because you're moving stuff around so much. As I've said, it's not a straightforward thing. So I'll go frames and transforms. I'm going to go rigid transform, bring this back, and I'm going to rotate this. So rotate it round. I'll drop it just beneath and tab it onto here. Now, the one thing that I realised this morning is so delicious, it's amazing, honestly. One thing I realised this morning, and it's what I'm going to take you through in just a second, is this relation is almost copy and pasteable. Once we get it ideally set up, you'll look and go, oh my god, this assignment actually is a lot easier than what he's told us it is. But it's not, it's still got difficulties in it, but that's where it is. So I go translation, I'm going to go Cartesian, and with my Cartesian now, so what I know is my X component needs to translate both gears, but their radii, and pluses it. So what you'll notice is I'm going back of here and I'm returning home. So what I do is I will go, I'm going to open the arguments. I always like to put arguments in there to give me an idea of what's been done. So I'll go 58.5 over 2. And I'm going to close that. So that gives us big gear. Then I'm going to plus, open the arguments, and we're going to go 18.5 over 2. I'm going to close that. And then I'm just going to translate that 40 millimeters. If you remember, that's the output shaft. That's where that's coming from. So we should be sitting in line. So if I click apply and then run. That needs rotating a little bit. What's important here is that these are relating. That it's given us what we're after. The starting position of that can be changed slightly just to make it better, and that's what that is. It's just the starting position, because one thing you should be aware of is it's actually not about the model, it's about the relation of what's going on. This is just to help us see what the hell we're looking at. Just to get it running, I'm going to go on to my Revolute joint. I should point out this is only the first layer of gears, but this velocity I'm going to put in, this velocity is what's going to actually power the entire thing out, and I can look at the input shaft and see what I would need, what type of torque I would need to actually get that out, if you will. So I'm going to go 1 rev per second and then run. So now his gear's running. We've got his gear. If we're going to relate this back, where we are now is we are here. So we have here, we have this, we have this. Now we've got the speed shaft. We've got to put in the speed shaft and then get this relation. This is not as straightforward as I was hoping it was going to be, actually. It turned into a bit of a pain in the backside. But it's not a biggie where we can't sort it. But this one bugged me a bit this morning. So what I'll do is go back to my actual model, and I'm going to add a connection here. This is purely because, excuse me. This was purely because what I wanted to do is, I'll just put this input shaft, output shaft. Just change that to output shaft, give me an indicator. And if anybody downloads this, at least they'll be able to follow exactly where I'm going with this and where it's come from. So my output shaft. Now with here, I've just realised I've actually not been deleting my frame set, so I'm just going to delete all my frames. It's because this model is going to get big, and it's not like the suspension that we can just get away with it nicely. So I'm just going to delete all out my addresses. So if anybody downloads it, you don't have to sit there forever getting this sorted. Double click into here, and I'm just going to set that there. We did talk about sorting out the output shaft, so I'm going to go damping. See where we got damping? So if I type damping, I'm going to set that to 0. So here, in here, my initial states, my initial mechanics, I'm going to type in damping. And it means I've got an overall governing thing that'll allow me to set it if I need to. Got damping and damping. Right. So, next piece on here. We're going to come back into the actual gear, and I'm just going to have a look at where the origin sits. I need something up here. This is purely because it's going to be how the gear is going to connect with the output shaft. You'll see in just a second why I've done it this way, because the way it actually sits in the simulation at the minute is like that. So if I connect these two together, this is where the output shaft's going to be when it needs to be over here. So I'm just doing it for alignment reasons. So I'm going to add in on this point here, and then add, I'll just call it connection. Use that as selection. Z's in the right component. Happy days. Apply and done. So now, this is what I discovered this morning looking at this and looking at this. It's absolutely delicious, it really is. So I'm going to drag this over, connect that up. I'm going to drag this over and connect that up. And I'm going to drag this over and connect that up. And just as a start, what I'll do is we're just going to change the shaft now and put it out to the speed shaft. So we're onto speed shaft, and then if I F5, that's onto the speed shaft. Just want to make sure that my speed shaft has got the origins correct. It doesn't, which is a bit of a pain in the backside, but it's not a problem. So what we'll do is go into our main connectors, and we're going to come down here and select this edge, and then apply, save, run, run. Now what I'll do just to make sure that this is working is run. I need to tidy this up because it's actually giving the wrong impression completely. We need to tidy up the actual run anyway, but we will get to it in just a second. Right, so, and then from there, what I can do is come in and now bring in, now bear with me on this, now bring in another big gear. So I'm going to bring in another big gear, connect it up, because if I come back, if you have a look, we're here, we've come along here, we're here, We have a big gear and then a small here. So it means the translation has to be different, but we can fix that. It's not a big issue. So I'm going to drag and drop another gear set here, into here, another small gear, into here. I'm going to bring across a revolute. Again, all the relation resides, all the same relation. Then I'm going to... now this is pretty cool. If anybody's got annoyed with the piston, this was a little bit of a personal finding this morning where I realised, I'm thinking, wow, yeah, it's obvious you can do this, but I didn't even think about it. Right, so this rigid transform translates home, yes? Yes. Right, so what if, now bear with me, what if you don't translate home, you translate to the next rigid transform, which translates home? In essence, making like a train, if you will. So what I mean is, if I bring this across, yeah, yeah, choo-choo to success. I'm going to bring that in, connect that up, and then connect this up to here. Now, the only thing that's different, if you remember, is we've got almost the opposite component sets here. And what we actually need to do is, if I go onto the old transform, or the original transform, see what we got here, and then if I go on to the new transform, and I'll just bring in the old one. Where have you gone? Where have you gone? There you are. Bring the old transform, and this is the new transform because it's transform 1. Need to be sure, or else I'm going to start deleting the wrong stuff. What I'm actually going to do is I'm going to say minus and minus. What it'll then do, translate it the other way, but still residing on this 40 millimeters. Oh, that nearly went wrong. That would have been very embarrassing. So if I come back, we'll go measure. Whoops. I'm genuinely measuring this now because I have forgotten what that value is. So I'll go here, and then I'll bring it back across. True value of 30. Oh, no. Yeah, 30. Okay, so what we do is come back, and we go translation, and we'll go true value of 30. Now we need to see if this is right. Might not be right. I don't think it is, but I'm just going to check it. It's not. This translation here has gone wrong, and that's a 10 millimeter translation. So what I'll do, oh yeah, violation. Yes, I know. God, it irritates me sometimes. If I bring that back and go 20 millimeters, then apply. And it's just taking into consideration the thickness of the original gear. What we can actually do is copy and paste. We can make that work to our advantage, which is sweet. Which is very sweet. So, let's get to the next piece. Now, moving along with it, we've now got one more layer to construct. We have here, and we're going to go here, this, and this. Now, these two gears are actually, this input and output shaft are actually different to everything else, as you'd imagine. So, we need to be aware of that. But we'll construct to here, and we'll get in the next big gear. So I'm just going to minimize that, and then come across. Oh yeah. Right. So what I'm going to do is I'm going to bring in these, right click, bring them across. I should point out, just so everybody knows, this isn't the assignment. This is just a gearbox that I found this morning, and then I rigorously checked to make sure it wasn't a load of crap. And it's not so bad, it's actually pretty good. Then emulating the exact same process from here. So what we're going to do is bring that across and then connect up our next gear. So let's just run it, see how it looks. Oh yeah, you know. We do need to tidy this up. It's all over the place, but we can fine tune this as much as we see fit. So on a big gear, and then we're going to move to a little gear. So again, I'm going to copy that in. And ironically, getting these relationships working right is probably a little more tricky than the Ducati. I was playing around with the Ducati this morning after I got this one nicely working and thought, oh hell, this could do a bit more tricky. Right, so I'll go to my small gear. And if you remember, on this small gear now, this is our output one. It's a different one completely. And this is under, oh, hang on a second, what did I actually call this? Well, not what did I actually call it, what did he call this? He called this input gear. So I'm going to go input gear and F5. Let's just check where our, yeah, connections, yeah, I mean, yeah, that's just wrong. So I'm going to go to frames. Don't forget, this is a new type of design. That's where it's come from. That's why we got that. So I'm just taking from the top edge, just to give it that position. Use that selection. Then we'll go save, and now we've got a good connection point for it, which is great. So go apply and apply. Right. So again, using this idea of that we're translating from gear relation to gear relation to gear relation, what we can do now is connect these up. So I'm going to right click, bring that across, because the relationship now moves backwards. So if I come back here again, and you've got to keep in mind we've actually constructed this way, where we've gone here, then we did a counter, and then back here again. So it's the same relationship, if you will, as the original one that we've created. So we can just copy and paste that straight in. And then I can right click and bring in a final set here. Bring it across. Tab onto there. And then I actually just need one last piece now. So connect up to here, bring across. Whoops. That was me left clicking. I'm going to bring across, and let's just punch that into there. And this now becomes the output shaft. Just realised I have not been deleting them reference points. Need to do that. Check my referencing. Main sits there. I think R sits there as well, looking at that. Does R sit there? R does sit there. What I'd like to do is then remove that. Go with 5. Oh, hang on. That's wrong. That's me choosing the wrong one. Damn it. It's the input shaft I was after. Sure, I selected input shaft. Input shaft. So go on input shaft. I was just thinking, because the gear that we've just added is teethed. Toothed. So I'll go on to here. And there we go, we have that toothed area. And then if I check the references now, that's a little better. Not perfect, but better. So I'll go into main, and I'm just going to centralize here, because that's what we've been doing. We've been using that as a key point location. So I'm going to go apply, and then OK. And then just as a test, let's see if this sits in the right position. Shit! You sure it doesn't? So what did I do? That's what I did wrong. The last translation. Now on that last translation, if you remember, I copied it, thinking, yeah, that'd be fine. I copied it directly from the other translational point. So if I double click into my other translation, and now what I'll do is drop that to my 20mm, which is that measurement that I took from the smaller shafts. Then if we hit run, should give us a running gearbox. Like that. So it's a good start. Yeah, we need to tidy this up a bit. So is there any questions on that? Has anybody not got this running? Has anybody got their gears going crazy? Because it can go a little bit crazy when you're getting it running. What we can do with that is we can easily add the housing. But again, it's just aesthetics. It just looks pretty, you know. So assignment wise, if this was the assignment, really you wouldn't add that. I mean, arguably, if you wanted, you can even add in the bearings. But again, the bearings, we have a representation for it. What's important is that we suspend that shaft in the correct position. So we've now got that as well. Everything's now really there. So if I minimize that, and then maximize here, so I come in. What we've now got is layers, if you will. So if I was to just split this out a bit, so all this here is now our mid layer. I mean our first layer of gears. We get to second layer of gears, and then we get to third layer of gears. And what we essentially did is we used multiple rigid transforms to transform all the way back home by using the same orientation again and again, and just inflated it as we were going along, which is ace. So we first things first, I'm going to offer a bit more resolution on that. Again, it's very tight. So let's come in and then let's go solver. I'm going to make it tighter and go double of its initial. That is my cat. So come back and I'm going to hit simulation and then just run it again. Right, so we've now we're now looking at the overall finish. Right, 2 minutes. I'm going to kill my cat. I'm not going to kill my cat. I'm not going to kill my cat. I'm just going to go salt my cat. It'll be 2 seconds. Right, so back at it. What we're going to do is check the torques that are coming out. I think more particular here. I'm actually interested about what's occurring here. And I'm interested about what will happen if I change things, and I'd like to know the speed in which it's moving. So we'll do some angular velocity, or we'll do some angular acceleration, arguably maybe position or an angle check. Let's do an angle check, and then we can try and build up a scenario of what this would look like. So if this was the example of which I'd set, where we're trying to yeah. Now the way that it's looking, Damien, is just aesthetic, and it's purely because if I run it, the truth of it is if I bring it back, they actually don't. I mean, if you look at the way that they're looking, they're actually sitting embedding here. But if I essentially get the starting position of this to go by, I don't know, 2 or 3 degrees, it will just put it in sync. Now the reason I've not been fussed with it is because this system will just predominantly focus itself on the values that we've added. So it is purely, just like I say, it's an aesthetic thing to give us what we're looking for. And imagine if you were using this software and you didn't even have that running. That'd be a nightmare. Right. So, I'm going to use a transform sensor. That's going to allow me to track the speed of the output shaft. Then what I'm going to do is bring in my world. Obviously, because I just need that reference point. I know for a fact I'm going to use a power stream to Simulink converter, probably multiple times. I'm going to need a scope, because we've used that quite a bit now, so I'm going to bring in a scope. And for this, at the minute, I'm just going to stay with that for the moment, just for the minute. We're probably going to need to add more and more as we're going through. So I'm going to go here, and then I'm just going to tab, probably from here, and then, oh, let's complete that first before I get myself tied up. So, I'll put myself a world in, and that world just gives me that reference point that I can tag onto. So, I could take an angle. Give me rotation on the axis. Let's take a look at them. In essence, we want to see. So I've put in 2 revolutions per second, and what I actually want from this is I need to obviously convert it out. So what was it? What were we at? We were at 1 rev per second. Might have an issue with that because I'm just trying to convert it really, and right. So we bring that back, and now just running as normal. So obviously that's what you should be getting, something that's relatively smooth that runs like that. Then let's take a look at what it's revealing. Axis, and it's also going to make acceleration. Oh, visitor. Well, so I'm going to drop that out, and I'm probably going to do angular acceleration on the X. Is it on the X? No, it's on the Z, isn't it? So my rotation. Pull into inherent and just see, because it's now in a different, right. Let's slim that down a little bit and go from a single second. Yeah, we need a velocity on that, don't we? So the issue that we got at the minute that's more like it. So you can see the initial build on it that's coming. Now these are all so all over the place. There is no damping in this at all. It will just provide almost 100% of what it's meant to deliver on. And what I actually want to do is I want to look at this. I also want to check on this torque here, because this is my outputs and well, actually my input. So I'm going to go to sensing. I'm going to bring out my total torque. Oh, I can actually bring out position there. That's quite good. I didn't think about that. Bring that down completely. Come into here, and I'm going to bring out my total torque. No, it doesn't. What it does is, think of it as that if you're measuring say if you're dropping a mass spring damper, and if you're just measuring from the home of its position, and you're measuring and you're wanting to measure the actual mass itself, what the second world allows it to do is to just give it them two initial reference points, so you've actually got a point for a real measure, and you can go absolute or non-absolute, and that's all it really is. It doesn't really set as an origin. It's just because this is how I've initially constructed it, basing this from that reference point, and that becomes my ultimate world spot, and that's where that's coming in, and that's where that's been really introduced. So I'll come onto here, bring that down. Bring that across, and then apply, and then close, and connect that up as well, and then run. There's practically no torque coming out on that. You look at the combinations between the two, 1 to the -4. There's not going to be much there at all anyway. What we're doing, all we're simply doing, is we're grabbing it from one side, we're rotating it at 1 rev per second, and then it's giving us the out. Now, yeah, I mean, in essence, we could actually take them particular points, that sensing position, and use it as a feed. We could use that to feed into something else if we wanted. Really, with this, it's almost a way for me to cut it off, to stop it. We don't have to stay in that position. We can use that follower for something. We can use it to feed to something else if I wish. It's just a nice way for me to tab off and look at output results that it's generating. But yes, no, you're absolutely right. Right, so if I bring it back across, and what I'm going to do from here is I'm going to go into my MATLAB, and now what I want to do is I want to start looking at this under a level of damping. Now, this value was one that my professor in unit, who was Ian Sherrington, always referenced to us of that it's a good initial starting point to start designing your bearings, to start giving you your bearings. Now, you got to keep in mind, I am not considering material loss. I am not considering lubrication pressure. With this, it just allows me to say, right, the restriction on this is going to be where that's going to come from. So if I hit that, now there is new tools in here to allow us to consider a lot more of frictional force, which is great, because initially we used to have to model these and build them up and make our own blocks for it, but they've recently introduced that, which if anybody's interested in knowing more on the wear, on the tribological side of this, these tools here are brand new. I say brand new-ish. Here we have contact forces, frictional forces, and you've got some level of method for interface on it. You can use Navier-Stokes, feed that in through a method of your critical forces that come at your critical static friction, or your dynamic frictions, or your critical velocities of whatever it is. You can feed it in that way. It is useful. It still needs a lot of tuning, I think, but it's one step closer. So if I run it again, and then housing, and right, so this is what we're getting. So if I run it in the main sim, I run it in the main sim, yeah, I know it is, Damien, I know it is. Building Navy of Stokes on this is just 10 short of suicide a lot of the time. Building it's just absolutely mental. Right, so this suggests, under the present state of condition that we're running at, this level of damping that's present has actually left it solid. Which, am I even running at the right values there? So 4. I'm just going to drop it down. Look at that. So if I come back in again, see how we're here. Now the damping on this is so great that it's actually overwhelming it. I forget though, it's actually quite small, isn't it, this? So if I drop it even further, so it's practically running at hardly anything now. Now if you remember, that is our angle offset. It would suggest that we'd need to run this a little bit longer. What we're getting is still relatively low levels of torque that's coming out of that, which is surprising. So I'm just going to bring that back in. And even still under a shorter element, it's quite small, is that. So if I run it again. Look at these torques. The damping is actually overwhelming it. Now arguably, the positional tool that we're using, is that restricting? Not restricting. Is it not really giving us what we're after? So if I go back into here, and what I'm going to do now is go back onto my joint, because I am starting to get some interesting results. Now I'm going to go back onto my joint. I'm going to remove the target velocity. I'm going to go into actuation. I'm just going to feed torque in. So I'm going to go provided by input. So let's say we've now got something that's feeding into it, and now we're going to drop in a little bit further. So I'll come on to here, and now what I actually want to see is I want to see what happens if I do a signal build. As I've said before, a signal build's great. I can choose a continuous value, I can choose variational values, and that's why it's always my go-to tool. So we'll bring that back, tie that in, and double click here. So if I just add one in, I'm going to right click here. I don't want this one. Delete that. And this allows me now to just choose a value. So we're going to go Newton meters. It's going to be quite a whopper. So I'm going to push my Y up to, we've got 2 Newton meters, which is quite a bigger. Bring that across into here. I mean, it might be might be too big for what we're going to do, but we'll run it and then see how we go. So if you run it at 2 Newton meters, you should find that the gearbox runs nicely. So I'll just bring you back in to show you what I mean. Gearbox is running nicely. We're getting this nice, consistent, solid thing that's going on. I've now removed that joint positional movement. So if I come back into my torque outputs, wow, this chalky chunkiness all over it. That is not good. That's producing, because that is still implying it's coming out of the actual joint itself. So let's have a look down here. Bring that out at Newton meters. It shouldn't change much, but at least it'll put it into something realistic of what we're looking at. So you look at that. Under this state, I mean, obviously, we need to take a look at that as to where that's coming from. I still suspect this is coming from its resolution. I don't know what he's just said, but I'll find out afterwards. This is still suggesting that it's quite chunky. It needs further tidying up, really does. But look at that build. We're talking around 35, almost 40 Newton meters based on that level of damping. So if this was running at a standard, because I mean, if I remember, we weren't going massive, were we? But at the same time, you should keep in mind the gearbox is quite small. I mean, 2 Newton meters of this gearbox. I mean, let's just have a quick look at how big this actually is. So if we just take this shaft, this housing to this housing, it's what's its actual 70 millimeters. Yeah, it's we're probably running it a little bit quick, so I'm gonna just slow that down a little bit. Let's just take it a bit. Let's take it down a little bit. So I'm gonna go 0.2, because that was just crazy. It was practically exploding. Let's have a look. Yeah, so it's speeding up. So it's damped. It responds to it. We've got, if we look into here, we've got these key points. Torque starting to emerge. It's resisting against the torque. You can see where it's almost smoothing out particular points, and then we do need to tidy it out because that's very irritating. But then it does. I mean, it does still come in quite high. You look at that. This is at Newton meters. 35.35. It is quite high, and that pushes it out to around 4,500 RPM. Still not convinced it would run at that speed. So if we wanted to actually achieve, I really entertain myself with this, clearly. If we wanted to actually achieve that level of speed at this particular rate, and we were after 0.2 newtons to come out, to actually get it, we would have to run it at something to overcome the level of damping that to get it to. We'd have to run it at around 4,500. That's why this isn't the assignment, by the way. Yeah, so it's not the ideal what we're looking for. But, right, so if I just take it back a little bit, so I'm just going to make it a bit more serious, and let's just drop it right back. So, if I just slow this down, because I'm hoping this will give people an insight in just a second. If I slow this down, and make it something a bit more realistic. Now you look at what we're initially looking at. These are the two particular torques that's responding around that gear shaft itself. So the smoothing I was talking about, that overcoming of the damping. So my question is, and the question that comes out on the assignment is, if someone's complaining of a particular noise that's coming out of it, what could one of the possible reasons be? Where would this be actually making a noise if it was coming from somewhere? The reason I wanted to run so quick is, in essence, really thinking about what we've done here is the answer to that gearbox. Really thinking about what happened here is why they put out the gearbox, Ducati looked at it, sent it back and said it works fine. Because technically, if you look at our gearbox, it does work fine. But what's the one thing that could work on this? The truth of it is the damping. Is the material it interfaces with. I mean, don't forget, we did make these out of steel. But what if it runs up, and what if the way that it's restricting is beginning to cause resonance? If you're getting a resonance at a certain level of operation, the question is, would you get? Is there some type of evidence to support that you would get some type of noise, some type of knocking, or something like that? Is there some type of hard evidence that you could pull out of it? And if you build that gearbox right, the answer is yes, there is. Finding it is very tricky though, and getting that gearbox built is also very tricky. This has been Gearboxers, and as I said, this is a nice example for it, and I quite like this. What I do want to do is, if anybody has any issues with their models, please send them through to me, by the way. I will honestly take a look at them and give you some insight as to controlling it. The gearbox, as I've said, I think it's got something like 150 parts on it. You don't need them all. This was a simplified version of that process. So we knew we didn't want that. We knew we didn't want these. All that we needed are the key players that interface within it, and that is just to know where these sit. And if you're lucky enough to have any type of measurement or a CAD system, if you want, by the way, you don't actually have to use SolidWorks to measure. Oh, this is one thing. I just wanted to show this to, who mentioned it? Damien. You were saying earlier about how they look to be interfacing, and it's just because the way I've imported them, I've used how they were originally drawn. If I just shift this, it will interface nicely. So it's just to show you that that's where it's come from. Yeah. So, is there any questions on this? As I've said, I will stop this recording and I will encode this as ever, and I will upload this model example to Blackboard. You're more than welcome to rip it in bits, take a look at it, see what you think. You can tell you're getting addicted. You can always tell when somebody's getting addicted. Now it's a cracking question, so I'm just going to read it just because then it's recorded. How do you combine ANSYS and SIM multibody? Now, personally, I've always had a major issue with trying to combine ANSYS and SIM multibody. Now, I'm just going to quickly, as we're talking, I'm going to quickly show you this software, Damien, and I should say everybody. This software is COMSOL Multiphysics. COMSOL Multiphysics is a sister company to MATLAB itself. This software will directly interface with it. Now, if you're referring to what my PhD work was about, my overall dynamic construction sat here, and then what I was able to do is interface it directly with COMSOL Multiphysics. Because of these two relations, it is super easy to get them passing data backwards and forwards, because all you essentially do is you hard code a direct command of pose and direct and so forth. Now, I am told that ANSYS and MATLAB do interface, but personally, one second, I will show you. Personally, I've never actually had ANSYS and MATLAB directly. Now, if anybody's interested in growing their experience further, what I would suggest is the trouble is once you get into MATLAB, it's it's like a downward spiral. MATLAB File Exchange. This is an online community. This is like this is like MATLAB nerd site. It is awesome, absolutely awesome. A lot of people what they essentially do is, if somebody doesn't like something about MATLAB, you've got a lot of people on here who actually just make tools. They just think, oh, that'd be cool, and they just make it. And there is some rocking people on here. There really is. There's some great insights to certain stuff. If you're interested about the aircraft design community, you can join these communities, and you've got people doing crazy stuff. This is essentially what got me into data acquisition and looking at how I could do it, and then what in essence got me onto this. So this is one bit of work that I'm doing at the minute, but this actually shows we've been fascinated with studying the human body and studying how it can do what it can do, and we need, because we've been doing the exoskeleton work, we needed a way to be able to simulate the human body being deformed. So all we've been trying to do at the minute is basically get a human's torso to move as we want it to. Now, what we've been able to do with this is take it and then transfer this directly into MATLAB, apply the exoskeleton straight to it. When it loads, it's a big model. It's partly made of skin and solid structures. So when it moves, that's what we get. So we were just trying to look at the sitting up process, and what you'll see is it's even got a spare tire. It's a great bit of kit. Right, so on to the next. Yes, if you email me outside of here, I can probably help you with that. There is a lot of contacts about that. So yeah. It's not free. It's not free. It is. It's quite a pricey bit of kit, and at the minute, COMSOL isn't really used by industry. Now, this is purely because it is heavily physics based. So if you look at this, for example, if I just extend and show you how I've constructed this model, this area here is actually made of silicon, and this came from genuine testing. Now, the only way I could do that is if on my model construction, where I've got hyperelastic materials, to explain how the material will deform, and then I'm actually using what is known as the Mooning method for hyperelasticity. So you write in the equation where I've got solid, it refers to the solid structures themselves and how they deform. So in essence, what I'm actually doing is using volumetric strain, but actually writing in where that volumetric strain is applied within the model. It's an awesome bit of kit. However, industry is not the biggest fan because it moves away from quick answer results, and it really stays with the hard physics behind it. But all my PhD was in this, and hence why I use this. So I hope that answers the question for you. Right, let me close that and close that. Right, so closing with that. That is the gearbox. I hope you found it a benefit, guys. I really do. As ever, I am available on Teams. I'm available for chat, anything like that. I had a message this morning about simulating ball joints. I will create a short demonstration of that and how it works. I've just not had time to get that sorted yet. I will get that done. I think I'm probably going to do it outside of these live sessions because it isn't really a long thing to do. But once it works, I can show everybody how to do that. So I'll do that. I'll probably do that between now and tomorrow, and then you've got that too. Again, if there's anything at all, please get in touch. If anybody's curious, us staff weren't privy to the emails that you got yesterday about the extension. In short, Damien, someone like you, not much. That's an honest to God answer. You know, the assignment, your assignment for my spring damper, COMSOL would eat it for breakfast. And your approach towards it, personally, I think it was more of a COMSOL approach than a MATLAB approach. Because you focused more on the meshing procedures and particular meshing procedures. COMSOL will allow you to manually build mesh and literally say at particular points how you want a mesh to behave. You can even drop in an equation to move the mesh whenever you need it to under certain conditions. If you do decide to get it though, anyone tries to have a go with COMSOL, please let me know. I do have a lot of notes. I do have a lot of books as well on it. It is, like I say, it is good, but as far as employability goes outside of here, sadly, I wouldn't recommend it, because there's only, if you're interested in going to biomechanical, then yes, I would say use COMSOL. A lot of my friends from the biomechanical world, if you will, they all use COMSOL for doing some mind-blowing stuff. But if you're interested in going to the main industry, more places, BAE Systems, places like that, they don't really use it, and it is purely because of that. ANSYS really do own the market when it comes to that. Hence why you guys did ANSYS this year in so many different things. Right, shockingly, I didn't run over time. I can't believe it, I didn't run over time. I honestly thought I was going to. I thought it was going to be one of them where I was just going to go on and on and on and on, but I didn't. So that was actually really surprising. If, as I've said, if there is any questions, if you're unsure about anything, please get in touch. I'll get it sorted. And yeah, thank you for your patience in all this. It's been crazy as far as coronavirus. And I will speak to you all soon, guys.